Well, let's say that we have an object of mass. Here it is, the object of mass m naught, and it's traveling to the right with a speed v star, let's say. And so at t equals 0, we launch this object from some location at speed v star. And we want to know how far it travels if there is a force, let's say F naught, acting on the object to slow it down. So it's going to slow the object down, so the force is directly to the left. And we want to know how far it travels before coming to a stop momentarily. Of course, it will then speed up in the opposite direction, but we want to know how far it travels before coming to a stop. So at this point, all we have are the kinematic equations, so we can say x equals x naught plus v naught, let's call it v naught x t plus 1/2 ax t squared, and we know that this is okay because the force is a constant, and so the acceleration is also a constant. So what does this look like? Well, first of all, we can write, we want the distance traveled from its initial position. We could call this 0, but ultimately it's x minus x naught that we're looking for, and that's going to look like this. And this forces us to, we need to get these different quantities, so we know what this is, that's v star, and we don't know what this is, but we can get it from F equals ma, right? So ma equals F for the x component of this, so it's max equals fx. What's the force in the horizontal direction? Well, it's actually minus f naught, right? The left is negative. So we have minus f naught equals m naught ax, and ax, so we can solve for ax as minus f naught over m naught. And so our equation here, x minus x naught, or we can just say x naught equals 0, make it look simpler, is equal to v star times t. Ax is minus f naught over m naught, so we have a minus f naught over 2 m naught for the acceleration, t squared. And we notice that we don't have a t, so that forces us to go somewhere else. In fact, we have to go to the second kinematic equation, which says Vx equals V naught x plus axt, and use that in some way. We know what this is, we know what this is, but the question is, what's this? And we have to figure out that dynamically, the speed of the object at the time that we care about, that's the time when the object comes to a stop. So that reduces to that being 0. We don't want any old time. We want the specific time associated with when the object comes to a stop, and that means that the x speed is 0. So this is v star, and this becomes minus f naught over m naught t, and from that we can get t equals m naught v star over f naught. Notice, we have to be careful there because t is positive. All right, so we can kind of, if we bring this to this side, then this is also negative, and then the negative signs cancel, and then we can solve by multiplying both sides by m naught f naught, m naught over f naught, and isolate the t. So we get t, and we can plug this back into here and there, and we'll get the distance traveled, x or x minus x naught, but in this case, x naught was set equal to 0, so it just looks like x equals v star times, let's put a parenthesis here for this, m naught v star over f naught minus f naught over 2 m naught times t squared. So that's m naught v star over f naught all squared. And so notice that we want to be careful here because here we'll get exactly the same thing that we have here. The dimensions have to be the same, so it shouldn't be surprising that we'll get, right here we get an m naught times v star squared over f naught. We're going to get an m naught v star squared over f naught times some number here, and that number is going to be minus 1/2. Right, we have an m naught squared here, but that cancels with the m naught here. One factor of m naught cancels, so we get an m naught here. We have a v star squared that survives. We have an f naught here and an f naught squared on the bottom, so we get an f naught on the bottom here. And so we get, in fact, something here minus half of that quantity, and so we get 1/2 m naught v star squared over f naught. That's how far the object travels. And when we get to things like energy conservation, we'll see that we can get this in one line as opposed to 3 separate equations here, right? Here we needed to use the x equation, then we needed to go to the second kinematic equation, and then we needed to use F equals ma. So it's 3 equations to get our answer. That's because we went through time. That's a much harder way. When we get to energy conservation, we'll see that we can do this all in one line by avoiding time.